Okay, gang, we know that matter is made of atoms. And the atoms are made of what? The atoms have a central nucleus, say positive, and around that nucleus orbits, say, a little particle called an electron. And this carries the negative part of the charge. It's this little electron that carries the negative charge that makes up electric currents in wires. Electron. It turns out this and this, these charges are opposite, and which belies a fundamental rule of electricity. Opposite charges attract, and like charges repel. Repel, that's right. And so the negative charge is being attracted to the positive charge and whirls around, round, round. In a very loose sense, and almost an incorrect sense. But we can think of it like a sun here and a planet going around and around and around. The force that holds a planet to the sun is the force of, we don't understand it very well. We have a name for it, begins with G. What is it? Gravity. And the force that holds the electron to the proton is the force we call, begins with an E, ends with an L. Electrical. It's the electrical force. So there's an electrical force between these two. Now we normally say that that atom has no net charge. Do you know what I mean when I say no net charge? There's as much positive as negative. In fact, if I had another charge, like a charge over here, a negative, this negative charge over here wouldn't even see that. It wouldn't sense it. It wouldn't sense it because this negative charge is what? Being attracted to the positive, but is being repelled by the negative. And the distances are about the same. So it turns out it's a wash. So a charge over here doesn't notice electrically this atom over here. So the atom is neutral. So we have a neutral atom. But let's suppose this charge is closer, like over here. And let's suppose it's part of another atom, like another hydrogen atom. This charge here now is closer to the proton than it is to the electron. So there's an attraction to the proton, a repulsion over here, which is not quite as big, it's a little further away. So we have now a net attraction. And do you know what happens to this atom here? It clumps together and it becomes a molecule. When you study chemistry, you'll study about the different bonding forces. And all those bonding forces you study are, guess what? Begin with the E. Electrical. They're all electrical. You are held together by electrical forces. Electrical forces comprise all the bondings that you have in chemistry. It's simply electrical forces. And these forces behave in a way very similar to the way that gravitational forces behave. Remember we talked about the force of gravity? And we said the force of gravity, there was a force in the universe that was proportional to the mass of one object, the mass of another object, divided by the distance square. Remember we talked about that? Well, physics is neat, gang, because guess what? It turns out there's a force that's very much the same between electrical charges. And that force depends upon the quantity of charge on one object, the quantity of charge on the other object, and depends on the distance square. Isn't that neat? Whip, whip, same, same. Which is one of the nice things about physics. Things that seem so diverse really have a commonality. And so this is called Coulomb's law. Coulomb's, named after a man about 150 years ago by the name of James J. Law, right on, okay. And Newton's law of gravity is named after a dude named Gravity. Okay, we got it. Okay. But we have these two things here. And all Coulomb's law says is, hey, the force of attraction or repel, one difference. Electrical forces can attract or repel. So you can shield out electrical forces. Gravitational forces only attract. There's no way to shield them out. But you can shield electrical forces. But it just simply says the amount of attraction or repulsion depends upon how much charge you're talking about and how far away the charge is. If they're very, very far away, then the force would be very, very weak. If they're close, 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 the force would be strong. Just exactly what you would expect. The same thing you'd expect with planets in the universe. Planets very, very massive, more force of gravity. Close together, more force of gravity. Same type thing with electrical forces. Any questions at this point?
Wouldn't a minus be part of the constant of proportionality for the electrical force?
I haven't even talked about constant of proportionality, but do you know what Lee is talking about when he talks about the constant of proportionality, gang? Remember the constant of proportionality for the force of gravity? If you took the force and divided it by this, you'd always get the same number. And that was that big G, 6.67 times 10 to the minus 11th, okay? That was the constant of proportionality. Over here, if you take the force between a couple of charged particles and divide that force by the charges and the distance between, you'll get the same darn ratio no matter what setup you talk about. And that's the constant of proportionality, and we call it K. Over here we call the constant G. Now we don't talk about a proportion. We talk about an exact equation where G and K make this side and this side newtons, newtons. Same. Other questions?
Yeah, if in the center of an atom you have more than one proton, which are two positive charged.
Yeah, this is for a hydrogen atom now.
Yes.
Let's suppose I had a helium atom. Now I've got two protons. Turns out there's two neutrons there too. And you know what's going to happen to the space over here? Take one guess. Everyone. This charge out here now sees two protons tugging on it. How many say it'll be pulled into a tighter orbit? How many say, no, it'll stay the same? How many say, no, it'll be pushed further away? Check your neighbor. How many say it's going to be tighter? Yay, that's right. And it turns out for a helium atom, the helium will hold the electron tighter. Furthermore, it will hold another one too. The fact that it holds another one makes it a little bit bigger, okay, because it's repelling over here. But a helium atom is smaller. And it turns out a helium atom won't gang up with any other atom. So there's no such thing as a helium molecule.
We have two positive charges right next to each other like that. How do you deal with that?
Why don't those two positive charges repel? Why don't they repel? Look how close they are. They're right up against one another. Why don't they repel? And let me say this. The electrical force is awesome. It's a billion times stronger than the gravitational forces between these particles. Billion. So there's an enormous electrical force tending to repel them. And why don't they simply repel? Well, it turns out you got to get to the last chapter in the book. And the last chapter in the book, you find out, honey, there's a force even stronger than the electrical force. Yes, there is, but only up close. And that force is called the strong force or weak force? Strong force. It's called the strong nuclear force. And there's a strong nuclear force that holds these things together in spite of the electrical repulsion. And later on, you're going to learn that when a nucleus gets too big, and these charges are far away, the nuclear force holding them together is weak compared to the electrical force, so they fly apart. And we'll learn that those atoms are called radioactive atoms. And all that has to do with the electrical forces between the nucleons. So there's another force that we haven't talked about that overwhelms the electrical. Any other questions at this point? Let's talk about charging. Here's a piece of cat's fur. It's for science. And here's a rubber rod. What I'm going to do is I'm going to rub the rubber rod against the cat's fur. Now what I'm doing... I don't know what that is. But anyway, what I'm doing here, gang, is what? I'm rubbing electrons from here onto here. And you know why? It turns out every substance is holding its electrons, yeah? How many say, oh, all substances must hold their electrons with just the same force? Coincidence of coincidences. No way. That's not true. Different things will hold electrons with more force than others. And guess what doesn't hold electrons very good? Begins with F, ends with R. Got a U in the middle. Try it. Fur. Or your hair. Okay. Guess what holds electrons very nicely? Begins with R, ends with ubber. Rubber, okay? And so I take the rubber and I scrape it against the fur. What am I doing? I rub electrons from the fur onto the rod. Now, the rod has more electrons than before. You people in the front row, can you see those things? Hula, hooba, hooba. Follow me, I'll make your crops grow. Hey, boom, okay. It turns out, no, I'm kidding around, but there are more electrons on here than before. So I say this is charged. Now, you got to tell me, negatively charged or positively charged? Neighbor. How many say negatively charged? All right. That's because the electrons themselves are negative. And by the way, do you know who was the one who gave us the idea of negative and positive charges? A first-rate scientist with a worldwide reputation in science. His name was B.F. Benjamin Franklin. That's right. Benjamin Franklin was noted as a first-rate scientist before he became a statesman for the 13 colonies. Benjamin Franklin did a lot of work in electricity. Benjamin Franklin is said to be the Isaac Newton of electricity. An enormously prominent scientist in his day, before the 13 colony type thing, and before signing the Declaration of Independence. Ben Franklin, he did a lot in electrostatics. So this then is negatively charged, and the cat's fur then would be positive there, which, by the way, underlies a very important principle called the conservation of charge. And the conservation of charge simply says that, hey gang, whatever charge you got, that's what you got. You don't make any more, you don't make any less. All you do is transfer it from one place to another. It's like maybe a brick road. There's so many bricks in the road. Now I take some of the bricks off the road and put them on the sidewalk. What's the total number of bricks I have before and after? The same. I've just put them from one place to another. And every brick on the sidewalk is matched by a hole in the road. You see that? So we're just taking from one place and put another. So if I put a certain charge on here, let's say a millionth of a coulomb. Coulomb is a unit of charge. If I put a millionth of a coulomb on here, and that's negative, what's the positive charge? A millionth of a coulomb positive. You see that? It just kind of makes sense. Okay? Let me get it's a ping pong ball painted with metallic paint. It's a conductor. Now what I'm going to do, the charge this rod up. I'm going to put some charge on here, onto the ball. And I think you can see that when I get the ball charged up. Watch this now. Repulsion. Did you see that? So like charges do what? Repel. Now let's suppose I take this glass rod and I rub this against a piece of silk. Now this is going to become what? Positively or negative? How many say, oh, I don't know. It's going to be positive. And we can find out it's positive by doing what? Bring it over here and sure enough, you see that? Opposite charges attract. Isn't that neat? Here's a nice little thing here. Let's suppose I take this down and put a non-conductor up there. Like this piece of popcorn from packing material, huh? Let's try this. Okay. Now, that has no charge at all. Okay, if it does, it would ground off to me. I would ground the charge. But it's non-charged. Watch this. Even though it's non-charged, see that attraction? It attracted. Oh, it attracted, then repelled. Why is that true, gang? Oh, it's attraction, 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 and pretty soon I get enough charge on there, so. But you see there's an initial attraction. Let me try that with a charge of opposite sign. Here's a positive charge. And it still attracts. Why? Why that's true is very interesting. It has to do with an idea called charge polarization. Let me show you what I mean. In this little piece of material here are little charges. There are just as many positives as negatives. When I bring the rod over, let's suppose the rod is negative. The negative does what? Pushes the negative part of those molecules over to one side and pulls the positive side, positive end, this way. For example, I have a little molecule like that. It will probably go like that, tend to point like this. Now the charges aren't moving through the material because it's an insulator. But the molecules in there, I can reorient and pull the positive side toward. And what do we got now? Now I get the positive and negatives. What do unlike charges do, gang? Attract. And sure enough, we saw an attraction. But that would work as well if I had the glass rod, as you saw. If I have the glass rod here, and I have positive charge, now what do? I take these molecules and flip them the other way. This is what happens. That's why you can take like a little piece of paper. Here's a little piece of paper here, okay? It has no charge. But I can charge up, say, the rubber rod, and I'll find out that the little piece of paper attracts. You see that? What I'm doing is I'm polarizing the charge distribution in the paper. And that's what I'm doing over here too. I'm polarizing it. And so now I have my little molecules like this. The negative is pulled toward, the positive further away. And since the positive is further away, there's what? There's less repulsion and more attraction because this is closer. Closeness wins. And so what happens? The whole device comes over. I can show you charge polarization in another way. I can show you that with this. Here we have a piece of plastic. This piece of plastic, it holds electrons very readily. I can just beat some electrons on here. And I do that. Okay. Now that's negatively charged, huh? Now I take this piece of conductor. It's a piece of pie pan, huh? And it's metal. Metal's a good conductor, easy for electrons to flow through, right? Especially if there's a little electric pressure. And guess what we're going to talk about later? Electric pressure. Anyone know the name of electric pressure? Begin with a V, end with voltage.
Voltage.
Voltage, very good. Okay, we're onto this stuff, not so bad, yeah? Okay. But notice I have a wooden handle. Why the wooden handle? It's a good insulator. Electrons won't flow very readily through a wooden handle. If I put this down on top of there, should this be charged? I turn it over, and it isn't. But what happens when I touch it with my finger? See that? See that? See the difference? Isn't that neat? Okay. So we find it's charged when I touch it with my finger. Let's take a look at this in more detail. Here's my piece of plastic material, and I beat a negative charge on there, yeah? And then I took the pie pan, and I put the pie pan on there like that. Okay? Now, what happens in that pie pan? Any free charges in that pie pan? Yeah. Any charges in that pie pan? Show me a piece of material with no charges. No way. There's charges in everything. There's atoms in the pie pan. And aren't the electrons loose in all metals? Isn't that true? So the electrons are going to be repelled by the negative plastic. So the electrons are going to be pushed to the top. And what's going to be pulled down, gang? Begin with the P. The positives, eh? I'm being careful to draw as many positives as negatives. Why? Because there's no net charge. And we saw that. If there were a net charge now, it would flow off through my body. Okay? But now there's none, and there's still none. No net charge. But what happens when I put my finger there? What happens then, gang? When I put my finger here, okay? When I touch it with my finger, then I afford a what? Why does it become charged? And let me ask you a question. When I do put my finger there, you saw it becomes charged. Why? And what kind of charge? Check your neighbor. Hey gang, I can show you that it's charged by lighting up this little lamp. Let me get this away now. No charge. If I touch it like this, boom, no light. No light. No light. All right, now let me touch it. Light. You see that flash of light? Did you see that? Let me try it again. Let me try it in the dark. Watch.
Now we saw it. That was nice.
Can you be seeing?
Yes, I can see it now.
All right.
Thank you.
So you guys thought I was putting you on, right? All right. All right. Okay. You could light up cities like that if you had someone keep doing that, right? We have a better way. Show you next week. Okay? Let's look at this device here. It turns out how much charge can be stored on those little domes there has to do with the radius of curvature of the ball on the top, yeah? The radius of curvature. What would happen if we have a large radius of curvature? Store a lot of charge or a little? Right here, gang. We're going to be seeing this, yeah? But how about if you have a small radius of curvature, like this point? It's a very, very sharp point. Very small radius of curvature. Will that store a lot of charge or a little? Answer begins with a L. A little. In fact, so little it won't watch this. When I touch the point this time, and I'll come over like this. Okay. I guarantee you, you will not hear any lightning. Crank this thing all night long, honey. No way. You know why no way? Because that point is so sharp the charge capacity there is so small that any charge that gets on there leaks off as fast as it gets on. So the charge leaks off, and here you see there was a that we prevented lightning from happening. And guess what these points are useful for, gang? On your barns and on your homes. Lightning rods, that's right. Let's look at lightning a little bit, okay? Here's the ground down below. Here comes a cloud. Maybe the cloud is all negative on the bottom. If it's negative on the bottom, guess what it is at the top, gang? Positive, that's right. And that cloud is going to induce a charge down below here in the ground. It's going to induce a charge. It's sort of like this cloud coming overhead. Here's the ground down below, yeah? And the cloud comes overhead and induces a charge down here. And what it's going to do is it's going to drive electrons down under the ground. And it's going to pull, in effect, what up? Hot plus. Now we have an interesting condition, gang. We have negative charge here, we have positive charge here, we have opposite charges like we had here with no lightning rod. What happens if the charge builds up? What happens finally? A boom! Huh? And what happens when a lightning cloud comes overhead? And it can't quite make it. You know why? That gap is too big. And you're out there playing golf. You're playing golf with your friends, huh? And you're out there and you take your copper shoes with the little cleats and you stick them into the soggy ground, right? Your friend says, hey, we better get out of here. There's thunderclouds coming over. You say, oh, just one last time. Literally one last time. You take the copper rod, okay, that copper club, and you lift it up in the air. And here you are right here, okay. And you lift the rod right up in the air. What does the cloud say? The cloud says, Santa Claus has come to town. I think I'm going to be making a little visit, right? Because now the path is short enough, and you get it. Many people get wiped out every year on golf courses because they find themselves the closest part to the cloud. And the closest part, nature's a little bit efficient or lazy, however you want to put it, and whoop, boom, they get wiped out. Even that happens with homes, too. If you have homes here, buildings. Do you see the buildings are closer to the clouds than the ground down below? Okay. Now this really people in the old days. Because in the old days, the tallest building in any community was, you guys know what it was?
Church.
The church, see? And it was thought that lightning was the wrath of God. Lightning was God's way of getting angry and a little bit upset, yeah? Now, what's the last building in town that should be hit by lightning, gang? The last one. Especially if no one wears lipstick, no one plays cards, and everyone is properly guilty for any pleasure they have, okay? And what building should not be hit?
People of the church.
But guess what building, time after time, no matter how little lipstick, no matter how much tithing, no matter how devoteful, no matter how much praying, guess what buildings were all the time getting belted by lightning? Begin with a CH. Church. Figure that one out. Yeah. That had a lot of people perplexed. Benjamin Franklin was a Unitarian. And in Philadelphia, Benjamin Franklin discovered these ideas we're talking about now, and he put the first lightning rod on the Unitarian. Now, you know how the Unitarians are. They can play cards on Saturday night. They can even drink liquor, okay? They can wear all the lipstick they want. They're thinking about the cosmos goes beyond those little concerns, right? But people thought that if any building ought to get hit, honey, it ought to be the Unitarian. And guess what? Never. The Unitarian Church didn't get belted. And one by one, the churches started putting up lightning rods. Because what's the primary purpose of a lightning rod, gang? Some people think it's to attract lightning. What did you see here? Is to prevent lightning. If you got a lightning rod in this church, what you do is you leak off this charge that builds up as fast as it builds on. So you won't have a positive down here and a negative. It'll leak off, you see? And what'll happen, the lightning hit over here, say hit the bar room over here, as it should be, right? The bar, okay, or something like that. But the church is spared if it has a lightning rod. So today it's commonplace to put lightning rods on structures. The primary purpose, to prevent lightning. Secondary purpose, if you get belted anyway, the lightning will be guided to the ground and spare the structure. Kind of neat, yeah? Question?
Where does the voltage come from for lightning bolts? I mean, it's not just that the positive and negatives are just there.
Well, how does this, your question really is, how does that charge buildup occur in the clouds? How does the cloud get negative on one part and positive on the other? And you know what? That is still being researched. The last I heard, there were still more questions than answers on that. Some people tend to think that in this day and age, we know everything. We don't know anything, really, compared to what's coming along, huh? We don't yet, it's my understanding, don't really have a clear understanding of why you do get that voltage difference in the cloud to begin with. There's a lot of ideas, as the rain falling down, friction rubs, and sort of thing like that, but there's a lot of other questions unanswered. So I don't know really why you do get that big difference in charge that causes this whole thing to begin with. There are several models for it, as I understand. Let's look at the granddaddy here. This is called the Van de Graaff generator. It's named after a person by the name of Robert J. Generator. All right, we be learning this stuff. All right. Now what we're going to do here, it's talked about in the textbook. It turns out this belt is going to carry charges from little lightning points here, deposit them up in here, and we're going to build up an enormous charge on the top. Let me show you what I mean. Notice I am, notice that I am keeping this closer to the dome than my head. Guess why? I don't want to put my head closer than this, all right? Now let me show you that that does charge. Let's try this, gang. Let's try this. Do we have anyone with nice, long, oh, my dear, back row, come. All right, what I want you to do, could you touch that? It's safe, it's all right. And I'm going to take this apart. Stand over here, honey. What's your name? Trisha. Okay, Trisha. Take your right hand and put it on the dome. Okay. It's all right. And I'll take this away, and you'll start to feel yourself getting charged. Shake your head a little bit. Okay. That's good. Good. Let it keep going. Good. A little bit like this. Okay. You see it starting to do what, gang? Starting to stand up. Could we have you people hold hands, please? Could you hold hands? It's all right. Hold his hand. Yeah. Hold his hand. Well, hold her hand, man. Hold her hand, too. She's nice. She's very nice. And hold her hand. And maybe you can hold back here. Yeah. Okay. Hold hand. Back here. Yeah. Okay. Keep going. Right across the hall. Right across. You get it? I feel it. Okay, thank you, Trish. Really nice. Okay, thanks. Let's hear it for Trish, all right? Okay. There's one more thing I want to show you, gang, is I want to show you that I can light up this lamp in the dark. Robert, the lights, please. The lamp is lit. When I hold it like this, no. But like this, yeah. This goes out, like this, lights. I've got a question for you. Lights, please, Robert. When I held the lamp like this, it lit up. When I held it like this, it didn't. Surrounding this dome is a very strong electric field. I've got a question for you. Where do you suppose the electric field is stronger? Close or far? Close. Won't I have charges in here more energized here than here? When we talk about the energy per charge, we're talking about a concept called voltage. Guess where the voltage will be higher? Here or here? When I hold it like this, I'll have a voltage difference. When I hold it like this, I'll have no voltage difference. When I hold it like this, you saw a current. When I held it like this, you saw no current. I wonder if there's a reason for that. We're going to talk about that next time. See you then. Physics. E.